Hey, today we're going to discuss what it means for a function to be continuous. Here's the definition. A function f is continuous at a point a if and only if the limit as x approaches a of f of x is equal to f of a. In other words, to compute the limit, all you have to do is take the value a and plug it into the function. We saw this already with polynomial functions. We saw that by the limit laws, to compute the limit of a polynomial, all you had to do was take the point where you're computing the limit and plug that point into the function. And we saw the same thing with rational functions where they were defined, which is to say that polynomial functions are continuous everywhere, and rational functions are continuous where they're defined, or continuous on their domains. There are a couple of subtleties built into this definition. In particular, the function f has to be defined at x equals a. If it's not defined at x equals a, then there is no f of a, and so it's certainly not possible that f of a could be equal to the limit as x approaches a of f of x. So the function has to be defined at a. And second, the limit as x approaches a of f of x has to exist. If that limit doesn't exist, then there's no way it can be equal to the function value at a. And so those two things are sort of lurking in the background of this definition. Those both have to be true. And then you also have to have the actual definition. They have to be equal to each other. The limit as x approaches a of f of x has to equal f of a. Okay, let's take a look at an example. Here's the graph of a function f of x. And see if you can answer these questions. Is this function continuous at x equals 2, 4, 6, 7, and 9? So take a moment, pause the video, see what you think. When you're ready, start it up again, and we'll answer these questions together. Is the function continuous at x equals 2? Well, no. For so many reasons. First of all, the function is not even defined at x equals 2. There is no function value there. Second, the limit doesn't exist at x equals 2. As x equals 2, as x approaches 2, the function is going to infinity. So the limit as x approaches 2 of this function is infinity, which is another way of saying the limit doesn't exist. So infinity, not a number. And so there are quite a few reasons why this function not continuous at x equals 2. What about at x equals 4? Here, the limit does exist. The limit as x approaches 4 from the left is 5. The limit as x approaches 4 from the right is also 5. And so the two-sided limit is equal to 5. The function is certainly defined at 4. F of 4 is 7. But the limit as x approaches 4 is not equal to f of 4 because 5 is not equal to 7. And so this function not continuous at x equals 4 either. What about at x equals 6? Well, the limit as x approaches 6 from the left and the right are both somewhere around, 4 2/3 or something like that. The function value is the same thing. It's 4 2/3 or something like that. And so yes, absolutely, this function continuous at x equals 6. At x equals 7, the function is not continuous because the limit as x approaches 7 does not exist. The limit from the left and the limit from the right both exist, but they're not the same, so the two-sided limit doesn't exist, so the function can't possibly be continuous there. Finally, at x equals 9, is the function continuous? Well, the limit from the left and the limit from the right both look like 3. The function value is equal to 3, and so the limit exists and is equal to the function value. And so, yes, the function is continuous at x equals 9. So, just to recap, carefully speaking in terms of the definition, a function is continuous at some point a if the limit as x approaches a is equal to f of a, the function value at a. But intuitively speaking, graphically speaking, you can see the places where this function is and is not continuous. It's continuous any place where you could draw the graph without lifting your pen. Here I go. I'll try to stay on this line, but I'll do terribly. I can't get from just less than 2 to just past 2 without picking up my pen, and so it's discontinuous at x equals 2. Same thing, as I go here, I have to pick up my pen to jump to the value at 4, so it's discontinuous at x equals 4. We looked at what happens at x equals 6. Sure, I can draw the graph right through x equals 6 without picking up my pen, and so it's continuous at x equals 6. Discontinuous at x equals 7 because I had to pick up my pen there, and then continuous at x equals 9 because I can draw the graph there without picking up my pen. And so there's certainly something funny happening at x equals 9 because there's got that sharp angle there, but that's a different property and we'll be talking about that later. Returning to our definition of continuity at a point, we can extend this some and say that a function f is continuous on some interval if and only if it's continuous at every point in that interval. This little notation right here, in particular this symbol right here, is a Greek epsilon that says a, an element of the interval I. So any point a in the interval I. So if it's continuous at all the points in the interval, then we say it's continuous on that interval. And so in terms of this new terminology, we've already said that polynomial functions are continuous everywhere, continuous over the entire interval of real numbers. And rational functions are continuous over their entire domains, wherever they are defined. Other interesting continuous functions include exponential functions, logarithmic functions, trigonometric functions, and inverse trigonometric functions. All these functions are continuous wherever they're defined, so continuous over their entire domains. Why do you care? Because it lets you compute their limits very simply. The limit as x approaches 4 of the natural log of x is simply the natural log of 4. The natural log is a continuous function, and so in order to compute the limit, you just plug in the 4. Similarly, the limit as x approaches 3 of the cosine of pi times x is just the cosine of pi times 3, or the cosine of 3 pi, and the cosine of 3 pi is -1. And so that makes that limit very simple to compute because the function is continuous. Before we go on to try some examples, let's take a look at the ways that continuous functions can be combined. In particular, if you have two functions f and g that are both continuous at some point c, then all of these functions, the sum f plus g, the difference f minus g, the product f times g, the quotient f divided by g as long as the denominator is not 0. These are all continuous at x equals c. I'll keep going. Some constant times the function f is continuous at x equals c. Raise f to some positive integer power. So if f is a continuous function, then f cubed is a continuous function. The 7th root of f is a continuous function as long as the 7th root of f is defined at x equals c. So these are all ways to take continuous functions and build new continuous functions out of them. And we'll see an example in just a second, but first I want to show you one more way to combine continuous functions, and that's through function composition. If f is continuous at c and g is continuous at f of c, then g following f is continuous at x equals c, where, just to remind you, g following f is just notation for g of f. So g following f of x, g of f of x. Okay, let's do an example. Let's see if we can compute the limit as x approaches 3 of the square root of e to the x squared minus 7. Well, the exponential function e to the x is continuous because exponential functions are continuous. X squared minus 7 is a polynomial, so it's continuous. And so the composition, e to the x squared minus 7, that's also a continuous function. And then we have the square root, or the second root of a continuous function, and so that's also a continuous function. And that tells us that to compute the limit, all we have to do is plug in 3 for x. And so we get the square root of e to the 3 squared minus 7. That's the square root of e to the 9 minus 7, or e squared, the square root of e squared, or just e. And so there's our answer. Okay, let's try a few examples. take a minute and see if you can figure out where each of these three functions is discontinuous. Shouldn't have too much trouble with the first two. The third one requires a little bit of work. Pause the video, take some time, do the work you need to do. It's great practice for the homework. And then when you're ready, start it back up again and we'll go through them together. You probably didn't have too much trouble determining that the first function is continuous everywhere except for at x equals 3 and x equals 4. The second function is a rational function, and so it's continuous everywhere on its domain, meaning everywhere where the denominator is not 0, so everywhere it's defined. And the denominator is 0 where x squared minus 9 is equal to 0, and that happens when x is 3 or negative 3. So there are two places where this function is discontinuous, 3 and negative 3, continuous everywhere else. The third function is a little bit trickier. First of all, to the left of 1, it's a line. It's the polynomial x plus 3. And so if you asked, is it continuous at x equals negative 47? Sure it is. It's the line x plus 3 at negative 47. Similarly, between 1 and 2, it's a parabola, which is a polynomial. And so it's continuous between 1 and 2. And the same thing, greater than 2, it's continuous as well. It's the parabola, it's the polynomial 5, the constant function 5. And so the only things you really have to worry about is what happens at 1 and what happens at 2. And to decide if it's continuous at 1 and at 2, you have to just go back to the definition and ask yourself, does the limit as x approaches 1 equal the function value at 1? Does the limit as x approaches 2 equal the function value at 2? And so if you didn't think of that approach, then pause the video now and take another moment and see if you can work this out, and then we'll do it together. First, we have to compute the limit as x approaches 1 from the left of this function. Well, for numbers less than 1, it's the top rule x plus 3 that applies. And so as we approach 1 from the left, we're approaching numbers that are getting closer and closer to 1 plus 3, or 4. And so the limit as x approaches 1 from the left is 4. On the other hand, as x approaches 1 from the right, it's the middle rule that applies. And if you take a number just slightly larger than 1, then you get something just slightly larger than 1 squared plus 1 plus 2. And what is that getting closer to as the x values get closer to 1? Well, it's getting closer to 1 squared plus 1 plus 2, which is also equal to 4. And so the limit as x approaches 1 from the right also equal to 4. And that tells us that the two-sided limit, the limit as x approaches 4 of h of x, the limit as x approaches 1 of h of x is also equal to 4. Let's see if I can fix that. Meanwhile, the function value at x equals 1, well, when x equals 1, it's the middle rule that applies because 1 is less than or equal to 1, which is less than or equal to 2. And you get 1 squared plus 1 plus 2, which is equal to 4. And so the limit as x approaches 1 is equal to f of 1. And so this function is perfectly continuous at x equals 1. What about as x approaches 2? Well, as x approaches 2 from the left, we have the middle rule that applies. So numbers slightly less than 2. So you could argue it's not the top rule because we're talking about very close to 2 but less than 2. And so if you plug in a number close to 2 but less than 2, you get something that's close to 2 squared plus 2 plus 2. That's 4 plus 2 plus 2, which is 8. And so the limit as x approaches 2 from the left is 8. And as x approaches 2 from the right, take a number just slightly larger than 2, and it's the bottom rule that applies, and you get that the limit as x approaches 2 from the right is 5. And so that tells us that the limit as x approaches 2 of h of x doesn't exist. And so this function cannot possibly be continuous at x equals 2. It's discontinuous at x equals 2 because the limit doesn't exist, but it's continuous everywhere else. Okay, those last exercises that we did put you in good shape to do your homework, but I like to ask questions like this on quizzes and exams, so let's just take another few moments and give this a try. See if you can sketch the graph of a function that's continuous everywhere except not continuous at x equals 1 and x equals 5, and that also has the following properties. The limit as x approaches 1 doesn't exist, and the limit as x approaches 5 equals 3. So in a minute, I'll ask you to pause the video and give this a try, but while you're thinking about it or while you're working on it, if you're not sure where to start, take a stab, sketch something, and then see if it follows these properties, see if it obeys these rules, see if these conditions apply. And if not, then go back, erase, and try to fix it. And so take a stab, see what you get, and we'll do it together. In just a moment, pause the video, unpause it when you're ready. Okay, we need the function to be discontinuous at x equals 1, and we need the limit as x approaches 1 to not exist. Well, the only way that the limit as x approaches 1 doesn't exist is if the limit from the left doesn't equal the limit from the right. And so we'll draw some function where here's the limit from the left, and here we come in from the right, and there the limit from the left is not equal to the limit from the right, and so the limit as x approaches 1 doesn't exist, and so there's no way that it could possibly be continuous at x equals 1. Next, we need the limit as x approaches 5 to equal 3, but we need the function to be discontinuous at 5. And so if the limit exists as x approaches 5, but the function is not continuous there, that means the function has to have a different value than the limit as x approaches 5. So as x approaches 5, we need the limit to be 3. So let's see if I can get this to happen. That's down here. There. Now, as x approaches 5, we're approaching 3 from the left and the right. We need the function to be defined, but not have the same value here. So let's just put it, let's say up there. And now I did it. Here's a function. It's continuous everywhere except at x equals 1 and x equals 5. The limit as x approaches 1 doesn't exist, and the limit as x approaches 5 is equal to 3. And of course, there are infinitely many other graphs of different functions that you could have sketched that would also have satisfied these properties. Okay, those were continuous functions. Take a stab at the homework, have some fun. See you soon.